ITC Lunch of the Week. As many of you know, last night, following the posting on the archive of a preprint, there was a lot of press coverage of the claim that the detection by the Webb telescope of dimethyl sulfide on this exoplanet indicates potentially life. And I don't know how much you follow that, but a lot of astronomers argue that this kind of a molecule, even if we improve the confidence from 3 sigma to 5 sigma, the molecule itself can be produced by many natural chemical processes. You find this molecule on comets, you find it in the interstellar medium. There was just a few months ago a paper on the archive about that with Webb telescope data. So it's not at all clear that this is a biomarker, but it's good that the subject is debated. So we are at a new era where molecules of that nature are detected in transiting planets. And obviously we will be waiting for more data and other types of molecules. And in particular, in this particular exoplanet, understanding whether it has a liquid water ocean and not a lava ocean, as some people claim. Anyway, speaking about exoplanets, we just had a wonderful ITC colloquium by Malena Rice from Yale, and she will continue the theme by talking about exoplanet demographics and architecture with the Habitable World Observatory, which is, I guess, planned for the mid-2040s. And obviously by then you will be a tenured professor, but some of us may not be around actually. So I think it's actually a very nice gesture that astronomers dream about projects that take decades to accomplish. It's sort of paying it forward to the next generation. And so we keep doing that. And then after Malena, we will hear from Saiyang Zhang from the University of Texas, over there, who will tell us about primordial black holes as potential seeds of supermassive black holes. Then we'll hear from Adrian Bayer from Princeton. Where is that? Oh, here he is. Who will tell us about field-level reconstruction of the cosmological initial conditions. And then finally, we'll hear from Cristiano Germani from Barcelona, over there, who will tell us about the unexpected shape of the primordial black hole mass function. So we have 2 talks on primordial black holes, one on cosmology, but the first one is on exoplanets. Please.
All right, thank you. So my name is Malena Rice. I'm an assistant professor at Yale in the Department of Astronomy. I gave the colloquium primarily about some of the research results on orbital architectures and things that I've been thinking about recently. So I wanted to, for this short segment, just turn to one of the other hats that I wear, which is looking at science cases for the Habitable Observatory and starting to actually define what the architecture of that telescope might look like, which is currently pretty up in the air. There's a lot that's being discussed for what HWO could look like, what it could do. So I'll talk a bit about sort of the overarching, what we know is planned for it to do, as well as what remains. And part of the reason that I wanted to talk about this today is because the science working groups that I'm part of have been actually instructed to, by early next week, define our sort of short list of priorities that we want to put forward and really ask the HWO leadership to take very, very seriously to make sure that the science cases that we want to accomplish are accomplished once they build the telescope. So if people have specific thoughts and have specific things that you really want the flagship mission that is coming in the 2040s to be able to do, that's starting to be defined now. And this is a good time to maybe come chat with me if there are specific things that you really want to advocate for. So just for a bit of background on HWO, this is the next flagship post-JWST that was recommended by the Astra 2020 Decadal. This is a mock-up of what it could potentially look like, but it's really, again, very up in the air. The things that we do know is that it would be 6 to 8 meters in size. It's sort of has been leaning towards smaller, but there's been a push for the science cases that you can do for a bigger telescope would make at least the scientists want it to be significantly larger, although there are budget reasons that could be difficult. And it will cover UV, optical, near-infrared wavelength ranges, and will be located at L2. So this is sort of the bottom line of what HWO is intended to do, is search for and characterize 25 Earth-like planets that could be potentially habitable. That can be interpreted in a lot of different ways, but the way that it is generally talked about is planets that are around sun-like stars in the habitable zone of their stars. And the main idea for how those would be detected is using a coronagraph. And so direct imaging of these exoplanet systems around primarily very nearby stars. But in addition to that, there's a lot of other stuff that HWO is intended to do. I'm going to make sure I'm on mute because I think there's sound that I don't want here. And so it unfortunately has a name that makes it sound like all it's going to do is exoplanets, but really HWO is intended to answer a lot of different kinds of questions, and there are people who are working on developing what the priorities should be for a lot of different axes. So this is just a couple of those. The current activities that are going on at sort of the uppermost NASA level downward is that the mission office was defined and was developed at the end of last year. And there are a bunch of us from the community who have been together with the NASA folks exploring the science, engineering, technology, trade space. Basically what we're doing is trying to figure out what are the science questions that we want answered, and then passing that to the engineers, figuring out what is actually physically possible, and then sort of having that back and forth begin very early on, such that we can develop this technology maturation plan and actually make this come to fruition by the 2040s. But what that means is that the science questions that we're defining for how to actually build the telescope around them are really being defined now. And so that's maybe the theory tie-in. This is the moment of deciding what science questions you really want this thing in a couple of decades to be able to answer. So there are a whole bunch of science working groups. I mentioned two of these actually are not exoplanets, although the first two are, simply because of that kind of high-level goal that is put forward by HWO. There are a bunch of people who are involved in this. So this is just the folks who are working on the Solar Systems in Context leadership team. So Evgenia, I know, is here at the CFA, and many of us are kind of regularly meeting a couple of times a year in person, as well as via Zoom, to actually build up these science cases. So these are the ones that Solar Systems in Context has developed, and I'm going to walk through a couple of the demographics and architectures ones. So I co-lead the demographics and architectures team with Jesse Christensen, who's at IPAC. And we have developed 4 of these science cases that I'll sort of talk through ours, but I do want to mention there are a whole bunch of others that other teams are working on that will hopefully encompass a lot of things that will push the bounds of what we think HWO can do. And so really what we want to accomplish with this is outline, what are our reach goals? What do we really think would be amazing to be able to answer at that point, which does require a bit of imagination about what things are going to happen ahead of HWO. And so what are going to be the interesting questions in the 2040s? So this is a couple of things that we think will probably not be fully explored at that point. So this is our sub-working group. It's a really fantastic team. It has been super, super fun to work with these folks. And these are sort of the science cases that each of them is leading that I'll briefly talk through what these are. So the first of these was really just this idea that somebody should probably justify that number of 25. So why 25 Earth-like planets? And so this was sort of starting to look at the trade space of also how many stars you actually would need to look at in order to get that answered. So this is led by Tansu Dalen and Romy Rodriguez, looking at what fraction of these small habitable zone planets exist in architecture similar to that of the solar system. So part of this is looking for those small planets that are in the habitable zone and how many stars you need to look at for that, at what wavelength ranges, what contrast to actually see those. But in addition, we would like to know a bit more about the architectures, and that's sort of what our team is pushing, is learning not just about those 25, but more broadly about the systems and what we can actually glean from learning more about the systems. So This is kind of a nice overview figure made by Tanzu that shows semi-major axis of planet as well as distance of the stars. And here you can see where the solar system lies if you put it at 10 parsecs. And on sort of these hashes, and in the color, you can see the angular separation of your planet as a function of distance. And there's a histogram that just shows there are 164 stars that were kind of identified as the top targets for HWO, and you can see the distribution of their distances. And so you can sort of figure out, what is the range of field of view that you actually need in order to actually see more than just the habitable zone planets, but ideally a bit more about the rest of the architecture of those systems from this type of schematic. Something that we and others have been thinking about is how to actually be able to use HWO and direct imaging to study binary star systems. So we're pretty limited to the local solar neighborhood for direct imaging, and there are some stars that could potentially be really great targets, but that are going to have binary star companions that will make it pretty tricky to actually suppress the starlight from your companion and see anything around the primary star. And ideally, you would actually consider those binary companions and hopefully learn a bit about planets in binary star systems as well. So one of the things that we proposed is that it would be great to get a sample of something like 50 systems that have some observations where there is a binary companion within 100 AU, and this is sort of the range of starlight suppression that you would actually need in order to get that for at least this initial NASA EXEP list of 164 stars. One of the other big science cases led by Sarah Blunt and Eric Nielsen is looking at how Earth-like atmospheres are changing over time. And so this is probably going to require a combination of precursor observations to actually get ages of all of these stars, which are not very well known for many of the stars in the local solar neighborhood, as well as actually then, once HWO is out, being able to see many of these signatures, but primarily ozone is one that's really being pushed for in the science case to actually get to the UV and have sensitivity to this feature that kind of has evolved over the history of the Earth as well. So this is actually a paper that's in review where Sarah did a bunch of these great injection tests showing injection recovery tests saying, okay, well, we'll assume some distribution of oxygen arising on these planets with some standard deviation, and then are you able to recover that within some useful precision for a certain number of planetary systems, for a certain age precision. And so from this, we're arguing that ideally we would like to have 20% age precision on these stars, which is going to require a lot of precursor observations, in addition to looking at ideally something like 40 stars that have Earth-like planets as opposed to 25, which would be a push, but is not hugely beyond what the mission was already planned to do. One other thing that we've been looking at is if you set your field of view too small, again, you're going to lose all your giant planets. And so pushing for this idea that it's also useful to have a sufficiently large outer working angle, which is OWA here, in addition to a smaller inner working angle to be able to see your systems as well as just individual planets. So this is just working out some of that trade space. This is another paper that's in review that is to come soon. So I will leave it at that and take any questions. I assume that was my timer, so. Yeah, so I'll start by saying I don't really have insider information on this. I'm part of the ExoPAG, and we had a meeting the day that that budget leaked, and they basically said we're not allowed to speak about the budget because I think it was fully informal. Like, it was not at all officially from the government at that point. Like, it had just been leaked, and they were not allowed to say anything as civil servants. As far as I know, nothing has stopped for HWO, and we're continuing to have regular meetings. We're continuing to push ahead as per usual. But yeah, possible concern. I personally am very concerned. I Googled how to call my senator for the first time a couple weeks ago, which is not something I've done in the past. It's hard to say. I mean, Roman has been cut a bunch of times and then re-added, right? And so it could, even if things in the next couple of years end up not being great for funding for HWO, that doesn't mean that it'll be killed long term.
Yeah, 20 years is 5 future presidents.
Yeah.
I have a question that is sort of more general regarding the HWO. So, how do you think, how strategically justified is it to put this flagship mission that is concentrated over just one science case, despite all the rest of the stuff that you're talking about? In the light of things, I don't know, if imagine AGI and the Galileo project discovered the extraterrestrial life here, this will immediately lose the importance, the science case of looking for other planets. So, are there any risk management strategies for things like this? So, would be there like changes in the instrumentation development in such a case, or something like this?
Yeah. So not all of the instrumentation would be geared towards specifically direct imaging of exoplanets, certainly. So there's discussion of having an IFU and having additional instruments that would be hopefully, really geared towards completely different science cases. There has been discussion about renaming the instrument simply because it really does imply that it's exclusively exoplanets, but not really at a very, we're definitely going to do this level, more at kind of the lower level of people saying, maybe we shouldn't call it that, because also then if you don't find a habitable planet with it, then that would not look great in the public eye probably. And so there's definitely some risk there. Missions often get renamed, and it can certainly shift in many ways along many axes. This is where it currently stands just based on the decadal survey, but that's not to say it isn't going to evolve. There's a lot of time for it to evolve.
And it was the highest priority in the decade?
Yes. Yeah.
So this was really the flagship of the decadal survey.
Yeah.
And if that doesn't happen, then what about the other recommendations? So this is really what the astronomy community decided to focus on.
Right.
Any other comments, questions? If not, let's thank Malena again.
All right. Yes. Well, timer starts. Given the tight constraints, I cannot say too many, but let me quickly introduce myself. My name is Saiyang, and I'm from University of Texas, Austin. I'm currently working with Supermassive, who used to work here. And for this talk, I'm going to talk about primordial black holes as potential seed for supermassive black holes. So basically, I'll break my talk into two parts. The first part will be supermassive black holes and the results from the latest GWC observations. And then I'll talk about the role of primordial black holes on the supermassive black hole seeding. And on the first part, it's more like the motifs for this particular project or the long-term projects that I'm being involved with. And at UT Austin, we have a group of people dedicated to the GWC study. So that's another motif. We have access to a lot of observation data. And what is supermassive black hole? To give a quick background, it is like black holes with mass larger than 10 to the 6 solar mass, and they will stay here. They won't just do nothing. They are a huge gravitational potential source, and during the process, will accrete the surrounding material through gravity. And during this process, it will form accretion disk, produce a copious amount of X-ray, and also a very good radio source. And here is like a black hole image from M87. And here, usually people detect black holes was through looking at the spectrum of the object. If some of the objects exhibits like broadline emission, indicating the existence of a fast rotating cloud around the center, then that might be a good indicator for the existence of a black hole near the center of the object. So since the launch of the JWST, the landscape for the black hole has been drastically changing, especially when we are able to observe black holes really early within the cosmic history. So this one in particular, UHD1, is observed at redshift of 10, and by redshift of 10, and when they are trying to deduce the mass of such black hole, it's already have the mass of 10 to the 7-ish solar mass. So people might wondering how such massive black hole form at such a short time period. Well, the cosmic time by that time is only like about less than 500 million years, but you have to have some black hole seed form at the initial place. So typically there are a few scenarios for the black hole seed formation. If you started out black hole with about 100 solar mass from the gas of the population 3 stars, they will form usually like a few hundred solar mass, and you really need to have this kind of a black hole to grow super efficiently, which is to say a black hole at a growth rate always at super Eddington rate to grow up to the mass or few orders of magnitude to UHD1. On the other hand, if you started out with some heavier seed, like from the DCBH direct class black hole, and you form a seed mass of 10 to the 4 to 10 to the 5-ish solar mass, and you don't really need to grow at a very efficient rate. So here is the problem for the black hole seeding mechanism, and the observation of such object naturally favors the black hole starting out from a heavy seed. So then those are like more recent interesting discoveries, which are called the little red dots, and little red dots are appear as as optically red object within the field of view. And it is characterized by its redness and extreme dense core, and almost like unresolved red dots. So this is how it's called. However, since the discovery of such objects, people has found like broadline agents within it, and the true nature of broadline emission within it. However, whether it is from stars or AGNs, its true origin is still remain highly debatable. So here comes to part of my work on the second part. So I'm the people like favoring or think about those are my from supermassive black hole origins, or primordial black holes might actually seeding such formation of such objects. So this is the particular work that being recently put on the archive, and I'm focusing on the role of primordial black holes on supermassive black hole seeding. And the primordial black holes that I've been focusing on is like a very massive seed, starting from like 10 to the 6 solar mass, which is the mass scale motivated by JWST observation, but also from some of the formation mechanism. So primordial black holes, just to give a quick overview, this is like a very general picture for the formation of primordial black holes, basically within very early time during the like radiation-dominated epoch within the primordial density fluctuation field. During the time where the horizon expand, like more regions are in causal contact, and once this region, over-dense region, reaches some critical threshold, it will self-gravitating and collapse then to form primordial black holes. And the reason or the motives for people start to get more interested is because of this particular gravitational wave event. And this is measured with two black holes, one with 60 solar mass and the other with 80 solar mass. And those black holes are really hard to be explained by the stellar origin, because if you have stars of that mass, they will just blow up to form peri-instability supernovae and leave no remnants. So since then, there are like an increasing number of primordial black hole paper after the discovery of this object. And now, finally, it comes to my work. I've been involving in the simulation. So here is like I want to study what's the structure evolution around isolated massive primordial seed and how it influences first star formation or first black hole formation. And well, this black hole mass 10 to the 6 solar mass is also scalable. If you like scale up or down by one or two orders of magnitude, the effect will be very similar. And here, the simulation suite I've been using is the Gizmo suite, combined with the n-body simulation, dark matters, and for the gas hydrodynamic simulation. And for the dark matter, well, since black hole is a huge potential source, it will accrete or attract the surrounding dark matter particles to as a coat to the black hole and form a dark matter halo. And on the other hand, for the gas, because primordial black holes, they are also black holes, they will accrete and emit a huge amount of radiation feedback. And during this process, the gas will exhibit much more complicated phenomenon. So here is like a snapshot where I take a redshift of 30, where we find that the first star formation, the condition for first star formation is ready. And here I don't know if you can see this tiny little red dots, is the position for which the first star formation takes place. And the black dots is the location of the black hole, and those arrows indicates the velocity vector of the gas. And well, you can see the location of the gas, the star formation site, which takes place in dense gas, but also cool gas, dense gas like above like 10 to the 3 per centimeter cube, but cool gas like about a few hundred keV, which is very like standard first star formation scenario, like by molecular cooling and the collapse of the gas cloud. And then initially we think we might stop there, let the first star form, but since we have the star formation recipe built within our simulation, we decided to let the system evolve and let the stars build around this system. And we see this assembly of a galaxy for lasting about 400 million years. Due to the computational hour limit, we stop our simulation at redshift 9. By that time, about like a million solar mass stars has already formed. And so if we like pick one of the snapshots at redshift 10, where like 1 million solar mass of stars already formed by redshift 10. And if we look at the morphology of the object, well, here our stars are like subsampled. There are much more stars, but here is to also show like the properties of the gas. Well, newly formed stars are still marked with red dots. You can see like newly formed stars are within the dense gas cloud forming clusters, whereas the older stars are like forming a more spherical shape. And here like black circles is the half mass radius. And if you compare with the distance scale over here, like 10 parsec. So the overall system is like 50 parsec in the radius. And this actually, if you link back to the little red dot object, they actually has a very good correspondence in terms of the size and in terms of the structure. So here's come to the money selling plot for our paper, because we have this one of the heavy seed scenario, but we also want to compare it with some other heavy seeding scenario by direct collapse black hole. Well, Junion, he went here like a few months ago. He was working on the direct collapse black hole related simulations. And so what I do is like I compare my simulations showing the solid lines with his simulations showing dashed lines. And we find that PBHs are extremely good at explaining those overly massive objects like UHD1 or Abel 2744, where you have black hole as the dominant component within the system. So here comes to the summary of my talk, and I'm welcoming any questions.
There are limits on these primordial black holes from gravitational microlensing, right? So which fraction of the dark matter can they make?
Yes, well, in our work, we didn't assume like a specific fraction because we are focusing only on one of them. However, we also thought about this problem, like because we are seeding the supermassive black holes, so we think that this primordial black hole should be, the fraction within dark matter should be about the same as the supermassive black hole density within the universe. So in the end, when it translates to the number within the dark matter, it should be like 10 to the minus 8 to 10 to the minus 9, which is like about the same level as the current constraints. And also in the other like previous work, I did the study of the structure formation with PBH. If we have too many like PBHs, then we probably see them already within our Milky Way halo. So there's another reason that we probably won't see too many. But our key message is that even if we don't see many of them, or even if few are present, they can still have some significant astrophysical effect, or maybe even observable effect.
Let's start with you and then.
Okay. So thank you for the talk. If you let your simulation keep running through redshift 0, are they still over massive black holes?
Right, that's a good question. Well, currently our simulation stops at redshift 9. However, if you want to run all the way down to the lower redshift, there's another consideration from the structure formation, because structure that they change is like on the dwarf galaxy scale, but if you run down all the way to the Milky Way scale, then there's different mass scale, and probably it's just merged with other massive halos, then probably one won't be able to tell the difference. And also, like I would also project if you are merging with galaxies where stars dominated versus the galaxy with black hole dominated, then gradually like more stars will build up around the galaxy, and the evolution track will become more closer to the present day and black hole mass to stellar mass ratio.
So the second question was that same one. But the first one is, what is the mass of the initial primordial black hole that you're considering?
Yes, we take to be 10 to the 6 solar mass, a million solar mass to start with.
That's at C, that's at redshift 9, right? Oh, no.
No, like
At redshift 1000.
1,000. Yeah, 1,000. Yeah, we start out from redshift 1,000.
Yeah, but the mass of the black hole at redshift 1000
Is
is
a million.
a million.
A million. Yes.
So it was made relatively late in cosmic history.
Yes.
That is after Big Bang synthesis, or when was the formation time?
Around although it depends on the formation mechanism, but around like electron annihilation time.
Okay,
Yeah.
so just before Big Bang.
Yes.
That's when
Just
we
before.
make a million solar mass. That's the mass inside the horizon.
Yes.
But the thing is, we don't know of any new physics at that scale, right?
Right.
So
Yeah.
it's a real challenge to imagine some phase transition that we haven't seen in the laboratory. That's one issue. Making such black holes will require new physics on an energy scale that we have probed in the laboratory. So we haven't seen any new physics.
Yeah, I agree. Like it's challenging to make the supermassive black holes, but if they exist, they can explain elegantly to many of the phenomena that we observe today. Yeah.
Any other comments, questions? Yes, please, Jesse.
Yeah, so how do you ensure that you make just the right number of primordial black holes, right? So even, let's say that this is the right mass.
Mm-hmm.
If this is intrinsic density fluctuations, that happens everywhere in the universe, right?
Mm-hmm.
Like, why do we not have Milky Ways with 10, 4 times 10 to the 6 solar mass black holes just floating around the galaxy?
Right.
Does that have friction?
That's actually a very good question, although our group doesn't specifically study that. Our motivation is more like, since we observe such interesting object, we want to see something could explain it. But your question is more like, how do they form at the first place, which falls out of scope of our current work. So I mean, this might falls more onto duty of the theory people, like who really like devise those kind of density fluctuation or primordial non-Gaussianities or like uncorrelated density fluctuation with the primordial Gaussianity fluctuation field. So, there are so many possibilities, and there's no consensus on the primordial black hole formation. So that's why we started out with one primordial black hole and let the system evolve. Yeah, but
Since this makes only 10 minus 8 or 10 minus 9 of the dark matter, it makes 10 to the minus 18 of the radiation energy density or whatever at very early times, right? So it's completely it would not have any effect on anything except the growth of black holes for now.
yeah.
Let's thank Saiyang.
Thank you.
Okay, hi everyone. I'm Adrian. I'm a postdoc at Princeton and at the CCA, and let's get straight to business. So the aim of the game in cosmology is you have some image of the universe, say galaxies or weak lensing, and you want to try and infer the cosmological parameters. And traditionally, what people have done is look at the two-point information. So you build a probability distribution of the distance between galaxies in your map, and you use this as a summary statistic to do inference. But with the new telescopes we have today, which probe the universe very high resolution, this isn't enough. This doesn't give us all of the information. And so one way to go beyond the power spectrum or the two-point information is to look at higher order statistics, and there's a lot of examples of things you could look at, but two that I've looked at is the halo mass function, so a histogram of the mass of halos in your universe, or the void size function, which is a histogram of the size of voids. And we found in simulations that if you combine all three of these different summary statistics, they have very complementary information, for example, for neutrino mass and sigma 8. So what this is showing is the three different contours of all the different summary statistics have very different degeneracies, and so when you combine them all, you can get very tight constraints on neutrino mass. So in principle, there's a lot of information to be found, and the question is, can we find all of the information? And so to do this, the approach that's been proposed is field-level inference, so to use all of the information in the field. And so the way this works is you start off in the initial universe, which we know is Gaussian distributed. So this grid signifies the pixels in the initial universe, which I've made quite big just for illustrative purposes. And then you have some forward model, which takes every pixel in your initial universe, and also the cosmological parameters, say sigma 8, omega m, and then gives you some final map. For example, the galaxies. But this could work for anything. You could do this for weak lensing. You could do this for the CMB. And another project that I've been working on, to take a slight detour, is making simulations which have all of these different observables correlated to enable future cross-correlations between different surveys. And I'm very happy to chat about this more later. To take an even bigger detour, happy Passover to anyone who's celebrating. If anyone wants to try some matzah for lunch and dessert, I have some in my bag, so come find me later. But back to galaxies. So the aim of the game in field-level inference is to take this backwards. So to go from the galaxies that you observe, reconstruct the initial conditions of the universe, and get the cosmological parameters at the same time. And if you do this all together, this should give you the most optimal constraints you can get on the cosmological parameters. But the struggle with this method is that you have a multi-million dimensional parameter space. You're trying to infer all these pixels of the initial conditions of the universe, which is very expensive. And there's various ways to deal with this. I'm going to speak about some of them very quickly now. If you'd like to hear more, come to my Astro AI talk on Monday at 11 a.m. But to give you an overview of some different methods and then focus in on one of them, let's start with explicit field-level inference. So this is when you actually write down an analytical likelihood, and then you can get an analytical posterior, and then you can do something like optimization to find the maximum of your posterior. And then people have applied things like the Laplace approximation to get constraints on cosmological parameters this way. And this works quite well in the CMB, maybe for CMB lensing when things aren't too nonlinear. But then for galaxy surveys where things are much more in the nonlinear regime, this doesn't work so well, and you have to move on to something like Monte Carlo sampling. And one thing that I've worked on in this area is using this new method called microcanonical Langevin Monte Carlo instead of traditional Hamiltonian Monte Carlo. And we found that microcanonical Langevin Monte Carlo is a lot more efficient than HMC. And one of the very interesting things about this is that it becomes more and more efficient as you go to higher and higher dimensions. So as you scale this field level inference problem up to actual surveys where you need to infer, say, 512 cubed or 1000 cube pixels, this new sampling method will be very useful. And this is a very exciting thing that I'm still working on now. But for the remainder of the talk, I want to talk about implicit field level inference. And so really, if we want to probe the small scales of the universe, it's very hard to do explicit field level inference because you don't really know what your likelihood is. And so in implicit field level inference, you use machine learning to try to figure out what the likelihood is and get samples without actually needing to know, without actually having to write down the likelihood. And so one way to do this is with diffusion models or stochastic interpolants. And this is something I've been working on with Carol and others here at the CFA. And what we looked at in our initial analysis is to see how many simulations do you need in this implicit approach to match the results of an explicit approach. And so this plot is showing the quality of the reconstruction on the y-axis and how many simulations you need to achieve that quality. The dashed lines is the explicit method, Hamiltonian Monte Carlo, and the solid line is this implicit method, stochastic interpolants. And you can see that stochastic interpolant line reaches HMC with around 10 to the 4 simulations. So that's kind of the number you would need, at least in this test example, to use this. But to tell you a bit more about how diffusion models and stochastic interpolants work, Here's an image of, say, a mountain on the left. And the idea of a diffusion model is you add noise to the mountain step by step until you end up with something which is basically pure noise. And the idea is to train a neural network to go backwards. So to go from this noise and then produce samples of different mountains or different images of Mount Fuji or whatever it happens to be, whatever you train it on. And so to show this in practice, the reverse step, here's a picture of me and Carol actually at Mount Fuji, but it was such a cloudy day, we didn't get a chance to actually see Mount Fuji, and we were very sad. But now that we have a diffusion model, here we are, Mount Fuji in the background. But you don't have to apply this to Mount Fuji. You could apply this to the universe. And so that's what we've been doing. And as you can see, we're pretty excited by that. And so the idea here is instead of mapping from the fog in front of Mount Fuji to actual Mount Fuji, you can map from the fog of the initial conditions of the universe to the actual galaxies or weak lensing, whatever it is that you see. So this is very exciting. But another thing I'm very excited about is some recent work that I've been doing with Liam Parker, who was an undergrad at Princeton and now a graduate student at UC Berkeley. And the idea here was inspired by Christopher Shalou and Daniel Eisenstein's earlier work about just using a CNN as a point estimate to map from galaxies to the initial conditions. And what we're interested in this work is looking at BAO reconstruction, particularly because right now with all the recent DESI results, this is a very exciting place to explore. So just to review what BAO reconstruction is, this circle represents the BAO scale in the early universe where it wasn't distorted at all and it was very clean. But then as the universe evolves, this circle becomes distorted. And you can see on the right, this peak, the BAO peak, smears out. And the idea of traditional BAO reconstruction is to use theory like Zeldovich approximation or perturbation theory to undo this nonlinear evolution and to try and reconstruct the BAO peak and then use this to do cosmology. But you can see traditional methods don't quite fully reconstruct the BAO peak. There's still some room for improvement between the solid line and the dashed line. And so the idea of this work is to take your galaxy field, do traditional BAO reconstruction on it, which is very cheap, and then to take both of these, feed them into a CNN in order to infer the initial conditions of the universe. And the nice trick about this approach is that because you do BAO reconstruction to start with, you already have the large-scale distribution correct. And so when you train the CNN, you only really need to focus on small patches of the sky. And so you train your CNN on these small patches and tile the entire sky, and this makes this approach very scalable for large volume surveys like DESI. And another innovation of this work really is that we're actually applying this to galaxies, DESI-like galaxies, while most approaches in the past have just applied this to nonlinear dark matter or maybe halos. And so to look at this more quantitatively, this plot is showing the cross-correlation coefficient between the reconstructed field and the true initial field. So closer to 1 means you're doing a good job here. And we're looking in redshift space, so these different line styles are showing you what the different angles to the line of sight, how they're being reconstructed. And so the gray lines are showing you what traditional reconstruction gives you. And the orange line is showing was what happens when you apply the CNN on top of that. So you can see the orange lines are always above the gray lines, and so this is doing a very good job. And then in blue, we have a line showing when there's no redshift space distortions. And so the best you can really hope to do in redshift space is to hit this blue line. And you can see that our solid orange line is very close to our solid blue line, and so we're doing almost as well as we can in redshift space. And so this is for a 1 gigaparsec box. So we trained on a 1 gigaparsec box and applied on a 1 gigaparsec box. But one of the selling points of this method is you can scale it up to an even larger volume. So we took a 3 gigaparsec box just because that's what was available. And we applied this method, and you can see that the cross-correlation coefficient for the solid line, the 1 gigaparsec box, and the dotted line, the 3 gigaparsec box, are both equally good on small scale. So you can scale up this method with no loss in performance. So that's very exciting. And then in terms of actually doing BAO information, this is a plot of the Fisher information in the BAO scale as a function of Kmax. And so you can see in the gray line, traditional reconstruction kind of tails off below around Fisher information of 10,000, while the orange lines from the CNN go much, much higher. So you can get a lot more information using the CNN approach than just traditional reconstruction. And then the solid line is kind of the ceiling of what you can hope to achieve. This is if you could actually measure the linear dark matter field directly. So there's actually a lot of room for improvement still beyond the CNN, potentially. And right now, we're actually working on feeding this through the full DESI pipeline and getting inference on the scale of the BAO, both in the perpendicular and parallel direction. And some preliminary results over here show that in standard reconstruction, you have this blue error bar over here, and then CNN approach slightly better, and then using explicit field level inference is doing better than that. But this is very preliminary, and I'm happy to chat about this more later. To talk about the future really quickly, we saw with DESI on its own, you get these constraints on W0, WA. If you combine with the CMB, things get even better. This is also true for neutrino mass. But maybe if we take correlated simulations like Half Dome I mentioned earlier and apply field level inference, we can get even tighter constraints. Thank you very much.
Question is, if you know that initially it should have been a circle, let's say, can't you use that as a boundary condition that you want to match the best circle? In other words, rather than reconstruct initial conditions, try to get to an initial condition that is a perfect circle. Is that possible? Did you ever take the boundary? Because that is used, for example, for the structure of the sun. When you try to solve for a solar model, you also have the boundary condition that dictate which solutions are allowed. So
Right.
suppose you did the same with the universe. You said it must be a perfect circle early on. Which perfect circle gives the best field, my take?
That's an interesting question. So it's not really the circle that you're trying to reconstruct. And I guess maybe the way that we put this into our framework is in the prior. So when you're doing the inference, your prior is basically saying that the universe is a Gaussian random field. And so that's kind of how we bake it in a probabilistic sense.
Okay, go ahead. Yeah.
For the implicit field level inference, I didn't understand what the diffusion model is actually doing. Is this just representing your prior, and is it a 2D diffusion model, 3D?
So, well, it can be whatever you want, but for the real universe would be 3D. And the idea is that you would map from this noise, so the initial universe you can think of as Gaussian random noise, because according to like standard model of cosmology, everything was Gaussian in the early universe, and then you map that to the galaxies. And then in the stochastic interpolant approach, the generalization that makes is that you don't need to assume anything Gaussian about the noise, and so you can really map from any distribution to any distribution. So you could say go from galaxies to initial conditions and just map those probabilities to each other.
Any other comments? Everything was clear. Thank you so much.
Thank you. Just click it in.
Where is the hole? Here. No working? So okay, so good. So I'm sorry, I will not have a so nice picture as you have seen before, because I will go more theoretical stuff. But I'll try to answer your question before about the statistics of primordial black holes and then the distribution of black holes in the universe. So this is a work done with this bunch of people. The close one to US is Ravi Sheth in UPenn. And so yeah, I'm going to talk about how we can actually guess with initial condition from inflation, for example, the number of black holes that are around us. But first of all, let me introduce a little bit primordial black holes and why I or many people think are interesting. So dark matter, that we need to find out what it is only interacting so far gravitationally. So the most natural object is obviously a black hole, because it just interacts gravitationally. So it could be other things, but this could be the easiest thing. So if black holes are big, as we were saying before, we will see it. Okay, so for example, from lensing, or if they come from phase transition, we were saying before, we would see it in the lab or whatever. So the best chance is actually that they are very small. Now, if this dark matter is formed by black hole, they are very small means really much smaller than the solar mass. There could be few of those, because statistically we can form some large, so you will be fine with that. But most of them should be very small, and if they are very small, so much smaller than the solar mass, then they cannot be of astrophysics origin. That's why we call it primordial black hole, basically. So they should be from some cosmological origin. So okay, so let's suppose that we have that we could form these objects that are cosmological, so they're very small, and so before they would be formed before structure formation. So for example, during the radiation epoch, and if they are formed during the radiation epoch, each time you form one of these objects, this object only interacts gravitationally, so it dissipates like the volume. Okay, it's like point particle in the middle of a thermal bath. So its energy density would scale like the volume, okay, because it's just matter. And instead, the radiation bath that is around would scale like a to the 4th, where a is the scale factor of the universe, okay? So that means that if we take the ratio between the black hole and the radiation, this will actually grow in time. So this is a very interesting point, because if the density grows in time relative to radiation, what happens is that at formation, we really need very few of these objects, okay? And that's the starting point, because what we're going to look for are rare events that happen during the radiation epoch. Now, so what we need is that occasionally we have, from the fluctuation that we know they form the CMB, for example, but from time to time we have a very large fluctuation that actually collapses into a black hole, okay? Now, let's suppose that inflation happened. We don't know, but we all assume that it happened, okay? So then the cosmological perturbation were generated by a scalar field, which we call it the inflaton. And so you know that if you have a scalar field, this doesn't have any preferred direction, okay? So if I take an isolated perturbation, this isolated perturbation looks spherical, because there are no preferred direction. If I take two of those that are close by, this will not be spherical. Okay, so this comes from the theory of peak theory, for example, for large-scale structure that we know, and the same for black holes. So a good assumption is that when we form these black holes, they are actually spherical. Okay, so the initial overdensity that will form this black hole is spherical, because we need very few of them. They are isolated, and then is generated by a scalar field, so they could be spherical. Then what we need to check for the formation of a black hole, we need to give some threshold, and this threshold would be given by its gravitational energy. Okay, so it has to be large enough to form the black hole, to form what we call trapped horizon, so everything will collapse into a black hole. What is the mass? Then the mass is basically, so we know, actually we can follow our Newtonian intuition. So the Gauss law. So the Gauss law is related to a surface of a sphere. Okay, it's the flux of the gravitational potential to a surface of a sphere, and the mass is related to that. So in general relativity, there is this funny thing that the sphere surface, not necessarily is related to the volume in a simple way, because the components of the metric are different, okay? So what we have to do to calculate the mass of the black hole, we really have to think about a sphere. And so if you take your metric, so this is spherically symmetric, you can always write in terms of what we call an area radius, which is basically the component of the sphere to calculate the surface or the perimeter. And the mass, the overmass that we need to calculate is the energy density of that large perturbation multiplied by, well, in the volume of this sphere generated by this radius, that is the radius of the surface, okay? This is called the Misner-Sharp mass, okay, so in general relativity. Okay, so then the gravitational potential is what we call, in the business of primordial black hole, the compaction function, which is nothing else than the gravitational potential as you would write down. It's 2 times the mass divided by the radius, okay? So it's nothing more fancy than this. And what happens is that when this gravitational potential eventually gets order 1, you form trapped horizon, and then you will form black holes as end of the story, okay? So the whole thing that we have to do is to understand what are the initial conditions for this gravitational potential such that at some point this perturbation will end up into a black hole. Now, if those perturbations are generated by inflation, what happens is that the initial conditions are always a super horizon scale. It means that they have wavelength that are way larger than the horizon at that moment, okay? So this is a sketchy thing of inflation. This is inflation, that we kick in radiation, some reheating in the middle. And so what we have to give is some initial condition where radiation starts. So we'll have this gravitational potential. This gravitational potential turns out to be frozen at super horizon scale. When re-enters the horizon, will start to form black hole or dissipate away. That's the threshold. So what happens is that then we calculate this gravitational potential at super horizon scales. Is obviously 0. So this is a sphere, right? So if I take the center, it's 0 mass. If I go at infinity, it's 0 because it's Friedmann-Robertson-Walker. So the easiest thing is that it has a maximum, okay? Now, you can imagine that the first shell that would try to collapse to form a black hole would be the point in which the gravitational potential is maximal, okay? And so the threshold that we give in numerical relativity, for example, is the value of this maximum such that we will form a black hole of mass 0. What does it mean? It means that if I have a little bit more, I will form a black hole with certain mass. If I have a little bit less, just dissipate away, okay? So that would be the threshold that we can calculate. And so we need to find an anomalously large value for this gravitational potential such that it will form a black hole. Now, cosmological perturbation, because they are quantum, they are also statistically distributed. Okay, so this is what we call curvature perturbation. So this is the Friedmann-Robertson-Walker. There is some kind of, well, there is this gravitational potential that modulates our energy here and there. And this is, oops, and this is statistically distributed. Now, if you calculate what I told you is the gravitational potential, which is actually fully nonlinear, it's full general relativity, but at super horizon scale, so I'm just doing gradient expansion, what we call, then the gravitational potential is actually only a function that is quadratic on this. For example, if your curvature perturbation are Gaussian, like we were talking before, okay, so then this compaction function, so this gravitational potential is a chi-square distribution, okay? So you can do the statistics, whatever it is. And so I want to insist that this is fully nonlinear. Okay, so this is full general relativity at super horizon scale. Okay, so then what we need to find then, we need to find this large gravitational potential. How do we do? We follow what people have developed in the large scale structure. So we take a sphere, okay, and first of all, what we do, we try to find, I'll finish. We try to find a point in space where this gravitational potential is larger, and then we try to find the smoothing radius where the gravitational potential is larger from that point in space. Okay, so we do these two things. So then we need to find the two constraints, the maximum in a point in space and the maximum of the gravitational potential, and there our gravitational potential has to be larger than the threshold. So so you know, now we have 4 conditions, and in order to have the maximal probability, they have to be uncorrelated. Okay, if they are correlated, we get less chance to get that condition. So that means that because the conditions are, one is at the center, the other one is far away from the center, better be that the far away from the center, this maximum, is actually as far as possible from the center, not to have interference between waves and get correlation of the conditions. So then what happens is that if, for example, we have a power spectrum that is flat, that is an infrared and UV scale, that means that our gravitational potential is peaked in the infrared scale, okay? Because the infrared scale is the largest possible scale. Okay, so then the mass spectrum, because the mass is related to the volume of the space that actually is squeezed into a black hole, then the mass spectrum would be peaked would be peaked on your infrared scale. So this would be your typical mass spectrum if you have two scales, a UV scale and infrared scale. Whereas, I mean, before this study, people thought that this would be related to, the peak would be actually at the UV scale because it's where the power spectrum, which is the variance of our statistical distribution, is peaked. Okay, so the conclusion is that it's statistically more favorable to actually generate few large black holes than many lighter, okay? And maybe a takeaway thing is that because you have to be careful about the infrared scale of your inflationary perturbation, this can be in the point in which you can have all the dark matter, okay? So for example, asteroid mass. But because you have also another peak of masses, you have to be careful that you're not going to hit the other constraints. For example, because those are very small masses, the other constraint would be the Hawking evaporation constraint. So if there are two small black holes, they will Hawking evaporate and screw up Big Bang nucleosynthesis. All right, thank you.
Black holes is that you really need to fine-tune, because if you take Pressure, which is the approach you are talking about, where you just look at the fixed statistics, then it will be exponentially suppressed for the unlikely events, and then you really need to choose a very fine set of regions to give you just the dark matter density, because that would be very unlikely that you get the dark matter to be comparable to the baryons or factor 5 bigger.
But I'm not sure if I would call this fine-tuning. I mean, it's like why an elephant is as big as an elephant and an ant is as small as an ant. You would not call this fine-tuning. So
the most likely outcome would be a significant fraction of the radiation converted. But we need something that is tiny of the radiation.
No, exactly the opposite, no? Because the most likely would be a very small, tiny fraction, because basically if you have the fluctuation coming from inflation, so then this is a perturbative theory. Because it's a perturbative theory, in order to have very large fluctuation, these are very exponentially unlikely, right? So the only thing that you have to fine-tune is to have a large enough variance in order to have statistically significant event that would form black hole. Now, if the fine-tuning you're talking about is this, then we have to talk about whether this is really a fine-tuning technically, meaning that whether I have a potential from inflation, and then this generates large perturbation, whether this quantum mechanically is stable or not. That would be a fine-tuning, a technical fine-tuning. Otherwise, it would be just a prejudice of human beings, I would say. So, and I think that most of these potential are actually stable, unless you do some tricky things, but quantum mechanically they are stable. I don't know if this answers your question, or partially.
Any other comments, questions? We're a little bit late,
Oui.
so anyone that wants to ask more can approach Cristiano.
Sure. Thank you. Thank you. How do I switch these? I think that's